Hello? Let's see, I've had tech issues all day, so I'm going to try to make this very efficiently to see if it works. So I'm going to talk about the last section of Chapter 3 and answer a couple questions that I got in class today. Section 3 is titled Bond Energies and Bond Enthalpies. This section seems to advise that we need to be attentive to vocabulary. Let's go through what our Chang book says about this topic. He gives us a reaction, a mole of hydrogen gas going to 2 moles of hydrogen atoms in the gas phase. The delta H of that reaction is given as 436.4 kilojoules per mole. Now this is a delta H of reaction standard because we're told that this dissociation occurs at 298 K and 1 bar. It's not the temperature that makes it standard, it's actually the pressure. But the value is given for 298 K. This is a measured lab value. Chang makes a point of calling it a bond enthalpy. Now remember, delta H values are heat transfers at constant pressure. So in this case, since it's a positive number, it means that the system will only go forward if it takes 436.4 kilojoules from the surroundings to make the reaction happen. He distinguishes the bond enthalpy from calling it a bond energy. He defines the bond energy as, quote, the energy required to break a bond between 2 atoms. This value, the bond energy, is 432 kilojoules per mole. That's the vertical distance from the lowest vibrational state of a hydrogen molecule, I don't have that written there, to the reference state of zero potential energy. In other words, when the molecule is bound and you want to break it apart so that the atoms are completely separated from each other, it requires 432 kilojoules. Chang says the measured value, the 436.4, should not be called the bond energy for 2 reasons. First, the system is doing some work on the surroundings because the 1 mole of hydrogen gas is becoming 2 moles of hydrogen. So if you recall the definition of enthalpy, delta H is equal to, the definition of H, enthalpy, is U plus PV. Delta H is equal to delta U plus P delta V if you do it at a constant pressure process. Another way of saying what delta H is to call it the internal energy change minus the work. Work is defined as minus P delta V, so that's why it's internal energy change minus work. So that's one reason why the enthalpy change is not what the bond energy is. The second reason he says that these values are not interchangeable is that the hydrogen molecules were storing some energy in vibrational and rotational modes that are not available to the hydrogen atoms. Those energies, those amounts of energy, are not relevant to breaking the bond, but they're there and they have to end up somewhere. And he says they're ending up in the enthalpy value, the delta H, that measured value. In other words, the hydrogen atoms are, quote, hotter because some of that rotational energy that was in the hydrogen molecules has to be put somewhere, and it's put into the translational energy of the atoms, even though that's unrelated to breaking the bond. A third energy term is called the bond dissociation energy. That term is used for Chang when the enthalpy can be assigned unequivocally just to the specific bond that the energy is measured for. So Chang uses it only for diatomic molecules. Here's a reason why it's problematic once you start getting to larger molecules. A measurement on water demonstrates his point. If you add 502 kilojoules per mole to gaseous water, you will break off a single hydrogen atom. It only takes 427 kilojoules per mole to break off the second hydrogen atom. So can you say that an OH single bond is 502? Or is it 427? Well, what Chang is saying is that when you get molecules involved, you have to do lots of similar bonds and take the average. Now, we would prefer not to have to use that method for the reason I mentioned in class. Those values are not as accurate because they're based on averages. Better values are based on using heats of formation. I want to take some time to talk about a comment on the question I got at the end of class. Why did we care about Kirchhoff's law? That's the law that allows you to figure out a delta H at a temperature other than 298. Why do we care about Kirchhoff's law? only in one of the steps in problem 59. That was the one at the end of class that I did a big Hess's law. And I said, that's a good catch. Then Colby asked the question. I think the author made a mistake. He missed a step. Here's what I think on this problem. So we were told to calculate the average bond enthalpy in water of an OH single bond. Now, by definition, those bond enthalpy values are in the gas phase in order to eliminate any influence of intermolecular forces. It's a more pure value. So bond enthalpies are measured in the gas phase. So what we wanted was to have a mole of water breaking up into 2 hydrogen atoms and an oxygen atom. That delta H of that reaction would be divided by 2 in order to get the average OH single bond. Okay? Now you might have said, well, why can't we just take the number that we got on the previous slide and divide that by 2? Well, that isn't what we were asked to do. We were asked to do this Hess's law version, assembling these different reactions. And if you go back to my notes on problem 59, we assembled 4 reactions. The first one I have written here is the reverse of the heat of vaporization. So if you recall, we applied Kirchhoff's law to it to do it at 373 K because those were the conditions that were given. I think the heat of vaporization at 298 is like 44 kilojoules. After we did Kirchhoff's law, we got 40.87, and then we had to reverse it in order to get the gas on the left and the liquid on the right. Remember, what we're after with these 4 reactions is to mimic that reaction up top. It's the second reaction that I think is a problem. That's where it's the reverse of the formation reaction of liquid water. Here, 1 mole of liquid water is going to 1 mole of hydrogen gas plus a half a mole of oxygen gas. So that number was basically taken from the back of the book, the delta H of formation of water, except with a negative sign. It gets flipped to a positive because we want the 2 water liquids to cancel. Now I have a double asterisk here. I'm going to talk about that on the next page. That's where I think the mistake was made, because that number is taken out of the table in the appendix. That's at 298. Doing that reaction at 373 is going to add enough of an error that you should do Kirchhoff's law. So now I want to talk about these last 2 reactions. And what I say here is I think the reason we don't use Kirchhoff's law on those 2 bond dissociation reactions is because the answer is on page 109. In the example in the Chang textbook that illustrates Kirchhoff's law, if you read the comment for the reaction, 3 oxygen molecules go to 2 ozone molecules, it says the difference in the delta H of reaction if you run it at 380 K compared to 298 K is very small. It's minus 0.97 kilojoules per mole. Note, the values are not appreciably different in the gas phase reactions. The increase in enthalpy from T1 to T2 for the products tends to cancel out that of the reactants. So in that example, he's essentially saying that 1 kilojoule per mole is not that big a deal and you could skip it. So let's see if his assumption, how his assumption goes for this reaction up here that I said was the reverse of the formation reaction. So let me use the next page to comment on the asterisk and the double asterisk. Okay, so what we did in class, if you look at that answer, it says 465.4 per mole for an OH single bond. Now, if you recall, we did use Kirchhoff's law on the vaporization term, and what we did is we lowered, the delta H of vaporization went down by 3.13 kilojoules per mole. And at the time, I said, correctly, I think, that the delta H of vaporization is going to be less at the higher temperature because that ambient thermal energy is going to cause, on average, there to be fewer hydrogen bonds on the liquid gas molecules, so you don't have to add as much energy to put them into the gas phase. So why didn't we do Kirchhoff's law in the double star reaction, which is the reverse of the formation reaction of water? My conclusion is I think we should have, and so I will. I looked up the heat capacity values of liquid water, 75.3, hydrogen gas, and oxygen gas. I rewrote Kirchhoff's law straight out of the book so that the delta H of the reaction at 373 was going to be equal to delta H of reaction at 298 plus the term delta CP delta T. So doing products minus reactants, I ended up, and then multiplying by a 75-degree increase and converting to kilojoules, I got a difference of 2.38 kilojoules, which made the delta H of reaction 283.4 instead of 285.8. So I think that was an error in the key and the example that we did in class, and this should have included Kirchhoff's law for that term. Now, a friend of mine, I talked about this, and he was familiar with the problem, and he actually did the math for those other two reactions that we assumed didn't need to be done, didn't need to apply Kirchhoff's law to, and he got less than 1 kilojoule per mole for those. So there is an error, but it isn't as large as it was for neglecting this term. I was also asked about question 3.50, in which I mentioned in class that the answer key had a different value. The answer key had the change in the delta H of reaction, so another Kirchhoff's law problem, and they said it was minus 197 kilojoules per mole. Clearly, that's got to be an error. We just went through some examples, and we're talking about single-digit kilojoules. It doesn't make sense that you would get an answer of minus 197 kilojoules. I don't know how they got that answer. In my opinion, I did it, and I got negative 1.97 kilojoules per mole. Somewhere, maybe they didn't multiply by the proper delta T. Maybe they did 1 degree instead of 100 degrees Kelvin. But let's see, that wouldn't make sense. That would make it even smaller. So I'm not sure what they did there, but I just wanted to answer that question. I hope this audio comes through. Please, I'll see you in class, and I'm looking forward to that. Bye-bye.